Hey everybody, this is Mr. Piercy, and what we're going to be looking at in this lesson are some inequalities dealing with two triangles and something known as an indirect proof. Now, first of all, an indirect proof is something that uses something in geometry that I generally say we have to avoid at all costs, an assumption. Now, usually when I say don't assume anything, it's usually in regards to don't assume that that's a right triangle because it looks like it's a right triangle, or don't assume that those lines are parallel because they look parallel. We can't make a conclusion about something's appearance. We have to have a reason for why we're going to say something is or is not whatever, parallel, perpendicular, uh, uh, square, rectangle, whatever. We have to have some reason why to draw a conclusion. Well, an indirect proof actually forces us to use an assumption, but in this case what we're doing is we're assuming that a desired outcome is going to be a false statement. And so in the process of trying to prove that statement is false, what you're going to end up with is a logical contradiction, where because you're contradicting something in your statement, you're essentially saying that it can't be possible, therefore the statement that you wanted to try and prove initially is actually true. This is a strategy that's used in philosophical debates. Ancient Greeks used stuff like this all the time when they're trying to prove an argument. Theoretical physicists use this stuff in thought experiments all the time, where you try to assume something is true and initially, and at some point, if you determine that there's a contradiction in your argument, then the argument is then invalid, so the statement cannot be false and therefore true. Well, moving on to uh, things that we're going to be doing in two triangles is something known as the Hinge theorem and the converse of the Hinge theorem. Basically, this is an extension of what I would think of as an extension of the triangle inequality theorem that you studied in a previous unit, or not in a previous section of this unit, I should say. The triangle inequality theorem, one of the things that it said is that the biggest side of a triangle has to be across of its biggest angle, and conversely, the biggest angle has to be across from its longest side. Well, here we're looking at the Hinge theorem, which says that if I have a triangle, or rather if I have a pair of triangles that have a pair of congruent sides and its included angle, well, where's the biggest side? Well, let's take a look at what we have here. We have two triangles. We have triangle, let's see, WVX, and we have triangle SRT. Well, angle R and angle V have to correspond to each other according to the way that the triangles are named. Now you can see that the triangles are not congruent to each other because the included angle here and the included angle here are not the same. But because angle V is larger than angle R, the side across from it, in this case WX, must be bigger than the side across from angle R, in this case ST. Those are the parts that we're looking at. And that's what we're concluding here, is that in this case, WX would have to be greater than segment ST. And the converse of that would be if I know that if I know two sides and its included angle is missing, then we want to know which angle is the bigger angle or which angle is the smaller angle. So looking here, we see that segment AC and segment DF are the same, segment CB and segment FE are the same. So we're looking at angle C and angle F as the included angle between those two segments. Well, looking at the side that is across from angle C, I can see that it's 12 units long. And the side across from angle F is 9 units long. Therefore, angle C must have a larger degree than angle F because it is across from a larger side. The only way it can be bigger is if it's across from a bigger side. So that's what we're looking at here for the converse of the Hinge theorem. It's a pretty straightforward thing, but the way that the way that it's written in its definition form is really kind of not the most obvious thing, I think. But that's really all the Hinge theorem is saying, is that if I have triangles that have, congruent sides from one triangle to the other, but the angle of one is bigger than the angle of the other, well then the third side has to be bigger or smaller than the other one. So here we're going to use the converse of the Hinge theorem. Well, remember the converse says we know that certain sides are going to be certain lengths. So now we're going to be looking to see, well, what do we know about an angle? So given that, and here, this is a typo, segment BC should be written as segment CB to keep the order of the corresponding parts in the correct order. How does angle 1 compare to angle 2? Well, here what we're looking at this angle here, and we're looking at this angle here, okay? So based off of what we're able to determine, oops, sorry, not angle A and angle B, or angle A and angle C. We're looking at this angle right here at 1 and this angle right here at 2. So the side that's across from angle 1 is 34, and the side that's across from angle 2 is a 33. Well, the bigger angle has to be across from the longer side, so that means angle 1 has to be larger than angle 2. And so that's what we're kind of looking at when we're trying to draw our conclusions here. Because segment AB is larger than segment CD, we have to conclude that angle A is going to be, I'm sorry, not angle A, but angle 1 has to be larger than angle 2. And that's really all we're looking at here when we're talking about the converse of the Hinge theorem. Now this is where things are going to get a little more interesting. Here in this example, we have a mall and we have two people that are leaving the mall. Car A leaves the mall and heads due north for 5 miles and then turns due west for 3 miles. Car B leaves the same mall, heads south for 5 miles, but then turns 80 degrees. And this is where I think I'm going to start losing some people. Okay? I don't think anybody is going to have a problem seeing that if I go north for 5 miles and then I turn left at a 90-degree angle, that I think everybody's going to be okay with the fact that this is 90 degrees here. Now here, this is where I'm going to start losing kids, is when I start going the opposite direction. Here, if I go south, when I turn 80 degrees from the direction that I'm traveling. So that's why this angle right here is my 80-degree angle. So that means this angle right here is going to be 100 degrees when I turn left there. And this is something that's very common. I want to just scroll down here for just a second. And this isn't like the prettiest picture that I was able to find, but it was the best picture I was able to find that explains here what we're talking about is actually something known as bearings. You'll talk about this a good deal. Well, I don't want to say a good deal, but you'll talk about it some in geometry. And again, in pre-calculus, you'll do stuff with vectors that you'll have to recognize that the bearing or the heading that something is taken is based off of a north-south direction, not necessarily an east-west direction. So that's all that's kind of talking about. So draw a diagram and see what we have. So here's a diagram that's been provided for you, and we're going to just kind of fill in the blanks here. Okay, so we go 5 miles north, we go 5 miles south, so those segments of the triangles are congruent to each other. Well, what the question is asking is who is actually further from the mall? And this is where this part down here at the bottom, let me pick another color, that's where this part down here at the bottom becomes really pretty important, because the angle that we're looking at, and what I'm talking about is this specific area here with the angles. The area that we're looking at is the angle inside of the triangle here, that 100-degree angle. Because if this angle is, here we have this segment and this segment congruent, this segment and this segment is congruent, but in one case we have an angle inside of the triangle that's 100 degrees, and then the other one we have an angle that's 90 degrees. So if this is 90 degrees here, then this angle inside of the triangle is going to be 90 also. Well, that means that down here at the bottom, the 100-degree angle, this has to be larger than this, because the Hinge theorem says that the largest side or the longest side will be across from the largest angle. And so that's what we're talking about. So that means that car B has to be further away from the mall than car A was. So I don't know, this is stuff that you would talk about when you're doing navigation. If anybody's ever seen Castaway with Tom Hanks, you know, when he's trying to talk about bearings and headings and figuring out how much of a square area that they're looking for is kind of based off of the bearing stuff that we're talking about here. But anyway, let's move on. So now we're going to talk about how to write an indirect proof. So the first thing that we want to do is identify the statement that we want to prove and temporarily assume that that's false by assuming that the opposite is going to be true. So now we're going to reason logically. We're going to go through, you know, using our deductive reasoning like we would in a normal two-column proof. We're going to reason things out, you know, as one logical statement leads to another, and then we're going to, at some point, identify that there's a contradiction somewhere. And because there's a contradiction, the assumption that we made about the statement being false can't happen. Therefore, the statement itself must be a true statement. And the example that I'm giving you here is not included in your notes, but this is an example that I'm giving you here of an indirect proof. Here we're saying triangle RST is isosceles with vertex angle R. So we want to prove that angle angle S is congruent to angle T. Now we know that they have to be congruent because we've already talked about the base angles theorem of an isosceles triangle. It says that the base angles of an isosceles triangle have to be congruent to each other. So for the time being, we're going to assume that that statement, angle S and angle T are congruent to each other, are not going to be congruent to each other. And that's what we're seeing here at step 2. This is that assumption where we're, for the time being, going to assume that the statement that we're trying to prove is false. And so we go through the following statements. RS and RT are congruent to each other because they're the legs of an isosceles triangle. Angle S and angle T are congruent to each other. Angle opposite of the same sides of angles opposite of congruent sides have to be congruent to each other. So here what we're saying in step 2 is that those angles can't be congruent. Here in step 4 we're saying that the angles have to be congruent. Therefore, that's where we have our contradiction. So because there's a contradiction between statement 2 and statement 4, that's why we're able to say that the negation of those two segments or those two angles have to be false. Therefore, the angles have to be congruent to each other and the statement is true. So here we're going to move on and we want to write an indirect proof showing that an odd number is not divisible by the number 6. So here we're going to just kind of follow through the step process that they're giving us because they actually did a really good job of explaining it here. So we're given that x is an odd number and we want to prove that x is not divisible by 6. So for the time being, we're going to temporarily assume that x can be divisible by 6. So that's the assumption that we make. So here that means if I say x divided by 6, I will get some number that I'm going to call n. Okay? So multiplying both sides by 6 in this case will give me x is equal to 6 times n. We're just doing some very basic algebra where we have x over 6 is equal to n. So we multiply both sides by 6 and we get x is equal to 6 times n. So moving on to step 2, if x is odd, then by definition x cannot be divided evenly by 2. However, that means that x is going to be equal to 6. So here, if I divide by 2, I will get, in this case, a 3n. Okay, well that means that I can actually divide by 2. I can divide by an even number. Okay, so here's where we're entering our contradiction. So this contradicts the given statement that x has to be odd, because if I divide an odd number by 2, I'm not going to wind up with a whole number. I'm going to wind up with a decimal of 1/2 somewhere. So therefore, the assumption that x is divisible by 6 is false, which proves that x is not divisible by 6. Okay, and that's really all we're going to be talking about. And I understand, I get it. I understand that this is going to be a little bit of a challenging concept. Some of us have struggled with proofs as it is, and introducing into something here called an indirect proof, I get it. It can be challenging, but just be patient and work your way through it and we'll be okay. Let me know if you have questions. That's what I'm here for, to help you out. So at this time, what I want you guys to do, because we're coming up here to the end of our lesson, go ahead and pause the video and answer the following questions on your own based off what we talked about in this lesson. And when you're ready, hit play and compare your answers with mine, see how you did. All right, so hopefully we have some good answers here. See what we did. So problem number 1 is based off of the Hinge theorem, or the converse of the Hinge theorem. We want to know what segment is longer, segment A or segment B. So if angle ADB, so here, if angle ADB is, I don't know, let's say that this is 100, is bigger than angle CDB, let's say that this is 80, then that means that AB has to be larger than CB based off of the Hinge theorem. Okay, because the longer side has to be across from the bigger angle. It's just that simple. Here in example 2, we're revisiting the mall diagram, except now instead of having the two cars that one went north and one went south, now we have another car that leaves the mall and goes 5 miles west and then turns 85 miles south for 3 miles. So we wind up with something that looks like this if you draw out the diagram, and this is very, very helpful. I think you should draw out the diagram. So we have the one car here that goes north 5 miles, and then we go west for 3 miles, and then here we go west for 5 miles, turn, and we go 3 miles, and then again this is 5 miles and 3 miles. Now remember, when you turn to 85 degrees, so you turn this way 85 degrees, okay, based off of the direction that you're going. But here, inside of the triangle that we make between the two segments that we made when we left the mall and when we turned, well, the third segment here, that 95 degrees, is inside of the triangle. So again, we want to know, in this case, write the cars in order from the closest to the mall from the furthest to the mall. So the smaller segment, in this case what we're looking for is kind of this segment here in red, here and here. Who is the closest and who's the furthest? And it's all based on whatever angle is here, here, and here. So the smaller angle means that they're closest to the mall, so whoever's in car A is the closest, whoever's in car C is the next closest, and car B is the furthest away. And now for the last one, suppose you wanted to prove the statement x plus y is not equal to 5 and that y is equal to 2. Then show that x cannot be equal to 3. What temporary assumption could you make? Now it's not asking you to go through the whole proof, it's just asking you to say what temporary assumption would you make. Here in this case, the temporary assumption, somewhere, there we go, the temporary assumption has to be that x must equal to 3. Okay, since this is what we're saying, this is like the given statement that we're trying to prove. In an indirect proof, we temporarily assume that that is going to be false, or it's opposite in this case. So if the given thing that we have is x cannot equal 3, then we have to temporarily assume that x must equal 3. So that's it for this lesson here. The Hinge theorem, talking about the biggest side and or the biggest angle across from either one. So the biggest side is across from the biggest angle across from the biggest side, and so on. And the indirect proof is where we're talking about we have to temporarily assume a given statement is a given statement is false, so that we can identify a contradiction, and based on that contradiction, then conclude that what we're actually trying to prove really is true. But that's it for now, ladies and gentlemen. If you have any questions, by all means, let me know what they are. Send me an email, leave me something in the comments. I'll be happy to help you out. But until next time, ladies and gentlemen, thanks for watching. Take care. I'll see you soon.